Hello, good morning friends. In the previous class, we learned about the different types of the sampling technique. That is impulse sampling, that is instantaneous sampling. Then we learned about the natural sampling. We learned about the flat top sampling. I will discuss flat top sampling in more further. So, to understand the flat top sampling, first consider this circuit. This circuit The circuit has two switches instead of using one switch. In the case of the natural and your impulse sampling, we are using two switches. One is known as a sampling switch and one is known as a discharge switch. Here, here the switches are made using the MOSFET or FET device. That device. I hope you understand the working of that device. Whenever the gate pulse is high, this is G1 or G2. The devices are on, and when gate pulses are low, the devices are off. Very basic, very simple understanding. Very simple thing is whenever your G1 and G2 is high, your switch is on, and whenever your G1 and G2 is low, switch is off. Okay, whenever the switch is on, the MOSFET or FET device behaves like a short circuit, and whenever the circuit is gate pulses are low, it behaves like an open circuit, very high impedance with no off condition. Okay, so you are giving input xt to the input side. This is your sampling phase, this is your discharge phase, this is the capacitor, and this is your output where you get the flat top sampled output. Okay, so just see only this part before this arrow, sampling phase, before the part of sampling. If this part is basically very similar to the ideal sampler. In case of the ideal sampler, you have an input, you have a switch, and then you get an output. Just see over here. Case of ideal. Okay, here input switch, it can be fed device, and then output. So you are getting this kind of output. Okay, impulse train multiplied by your input, you are getting impulse output. Okay, so here the same circuit, so we are getting the same kind of output after the switch G1. Whenever the G1 is on, you are getting the same kind of output of a impulse output. Okay, this G1 behaves like a short circuit whenever your gate pulse is high. Okay, so you are giving your delta t impulse impulse signal to this gate pulse. Whenever gate is high, input is transferred to this node, and whenever gate is low, then it's blocked. Okay, then this one is discharge region. Whenever, for example, this is getting, we are getting the output, the capacitor are getting charged. Whenever the capacitor is getting charged to up to the value of the xt, you are getting value across xt to the gt. But whenever your G2 is high, what is happen? It will have like a short circuit. The capacitor is now getting the discharge using this switch G2. Okay. Whenever your G2 is high, capacitor gets discharged. Whenever G2 is low, capacitor gets charged. Okay. This is the basic working. So you are getting a sampled output, sampled and hold output. First one is sampled output. Then whenever this discharge, it will hold. Output is 0. So sample and hold output. This circuit is also known as the sample and hold circuit. We will also learn in PAM signal, pulse amplitude modulation, kind of sample and hold circuit. So this was the basic working operation of the flat top sampler. You are having this impulse train, then multiply with this pulse train. You are getting, finally you are getting sample and hold output. The top is always flat. Top is flat. Instead, just like in a natural sampling, the top is taking the shape of the input, but here it is flat, so it has a very high noise because you are rounding off the top edges. So the noise is very high in this flat top sampling technique. Okay, I hope you understand the working of flat top sampling and this circuit operation. So now let us move forward for the some numericals. So we will going to learn some numericals associated with the sampling theorem and the Nyquist criteria. Okay, the first one is find the Nyquist rate of the Nyquist interval sine 2 pi. So this is a very simple thing, sine 2 pi t. So sine 2 pi t means it's like just like sine omega t. Okay, omega is equal to 2 pi here. Here you can see the solution. Here omega m is equal to given by sine omega t. Omega m is equal to given by 2 pi. But we know that the omega m is also omega is equal to 2 pi f. 2 pi f. Here f is equal to 1. We can see that f is equal to 1. So the Nyquist rate is f is equal to twice of fn. We already knew that f is equal to twice f. So twice of also Nyquist interval is 1 by 2. Twice of fn is 1 by 2 second is Nyquist interval. Very simple numerical. Now we will increase the level. Now the second question. Find the Nyquist rate and Nyquist interval of a sinc function 200t. Okay, now how we will solve this? Again, here omega n is given by 200 pi t. 200 pi omega m is equal to 200 pi. 2 pi fm is equal to 200 pi. Then twice of fm equals to 200 hertz. Okay, twice of fm is equal to twice of 200 hertz. So Nyquist rate is equals to twice of fm equals to 200 hertz. Nyquist interval is 1 upon 2m equals to 1 upon 200 seconds. Actually, here pi is not given. See very carefully, pi is not given. Okay, so that is why this whole calculation is there. We calculated twice of fm is equal to 200 of hertz because twice is 2 pi fm equals to 200 of pi. Okay, next question. Which of the following is the process of aligning peak overlapping, phase overlapping, amplitude overlapping, or spectral overlapping? The answer should be D, the spectral overlapping. We see in the previous slide that is aligning this last part. Understanding. Here you can see that this aliasing occur. So aliasing in occur in the spectrum axis. This aliasing occur in the spectrum. Okay. So the answer is B. That is spectrum. Aliasing is defined as a phenomena in which the high frequency component in the frequency spectrum of the signal takes the identity of a low frequency component in the spectrum, as we seen in the graph. Okay. Aliasing occurs if either of the following conditions exist: the signal is not band limited to a finite range and sampling rate is too low. Next question. Find the Nyquist rate and Nyquist interval of for the signal ft is equal to sine 500 pi t upon pi t. Okay, it's just like a sinc function. So how we will solve that? Here function is given by 500 t pi t upon pi t. So omega is equal to 500 pi, same procedure. Omega is equal to 500, 2 pi, omega m is equal to 2 pi fm. 2 pi fm is equal to 500 pi, pi to pi cancel, twice of fm is equal to 500 hertz. So Nyquist rate is fx is equal to twice of fm, that is 500 hertz. Nyquist interval you can find easy. Next question, find the Nyquist rate and Nyquist interval of the signal. Same signal but square term. So simply sine square, you have to solve this. Sine square is 1 minus cos 1000 twice of the 2 theta t. Simple method, simple trigonometric formula we are using. So here omega is given by the 1000 pi. So twice of fm is equal to 1000 pi. Twice of fm is equal to 1000 hertz. You will solve this. You will get the answer. Very easy question. Next question. Find the Nyquist rate and Nyquist interval for the signal 1 plus sinc 300 pi t. Again the same procedure. Omega m is given by 300 pi. Omega m is equal to 2 pi f. M is equal to 300 pi. Twice of m is equal to 300 hertz. Same procedure. Or we have to do the same thing in all the sample. Now this is a different question. Find the Nyquist rate and Nyquist interval for the signal given by rectangular of 200t. So see, so we see that here is a rectangular pulse is given, and pulse with frequency is given by 1 by 200 second. That is the frequency. since the signal is a finite duration signal, okay, it is not it's a rectangular signal time domain. Okay, the spectrum consists of an infinite frequency, hence the Nyquist rate is infinite and Nyquist interval is 0. Next is sampling frequency is given by 2000 samples per second. Find the Nyquist interval. So simple sample fs in this time the fs is given and Nyquist interval is this is given in this question. The sampling frequency is given. Listen very carefully, not message frequency. Sampling frequency is given. Okay, already fs is given. So one fs is equal to 2000. So t is equal to 1 upon fs, because fs is equal to twice of fm होती है. Twice of fm already is given. That is 2000 samples. So 1 upon 2000 is 0.5 millisecond. Next question. Next question. That is determine the Nyquist rate of the signal wave and determine the Nyquist rate interval for the signal minus 10 sin 400 pi t cos. Now these question number 11 and 12 will be performed by 2. Okay, this will be performed by you only. You have to find the answer for question number 11 and 12 in the next class and post me answer on Google Classroom. It is very important. Please post me the answer of question number 11 and 12 in Google Classroom. So today what we learned? Today we learned about the basics of flat top sampling. In flat top sampling, simple structure, simple circuit diagram. In simple circuit diagram, instead of using one switch, we have used two switches given in G2. The version of these two switches are made using the semiconductor devices like MOSFET or BJT. In this case, we are using FET. The working operation of FET is very simple. For N-type FET, if the gate pulse is high, device is on. If the gate pulse is low, device is off. So G1 is when G1 is on, this work as a sampling switch. Your input is reflected to the output. The input is reflected to this capacitor, and the capacitor will get charge up to the value of xt, and we are getting value gt equals to xt. That is how the multiplication is occurred. Xt multiplied by this. Here G1 is given by the impulse train. G1 is nothing but what the impulse train delta of t. Just like in the first case, that is ideal sampling. The xt multiplication with the delta t. Okay, you are getting an impulse output, perfect impulse output. Now this perfect impulse output we are getting across this capacitor. Now what is the role of G2? G2 is a discharge chip. Whenever you want to discharge this capacitor, you have to turn on this G2 switch. So we have to give a square wave to this G2 switch. Here we have to give the impulse train. Here we have to give the square wave. So square wave is given. So whenever this G2 is on, the capacitor is connected to a ground and get started. And that is how we get the flat sample and hold output across this GT, which is also known as this flat top sampled output, which is a PAM signal. We can also say that it's a PAM signal. For mathematics, now some numericals we have learned about the Nyquist rate and the Nyquist interval. Very easy numerical. Please go through all of these explanation also. And I have given two assignments, two questions, very simple questions, two questions. You have to perform this as soon as possible and post the answer on the Google Classroom. Thank you guys. Thank you.